So first things first, that is not a typo. Um, it, is, it is a tase. So first, like sort of the 10-second elevator pitch for ATS. It's an ML. It's got algebraic data types, pattern matching, all of that good stuff, tail calls. But you can write code that is as fast and uses as little memory as C. And it's also type safe. So at the end of the day, the initial 10-second hook is it's blazing fast and type safe. But I think more interesting than that, more interesting than the fact that it produces good code, is why. So there is no compiler optimization really. ATS does not have some amazing compile time magic that converts ATS code into efficient C code. The reason you get that performance is because it compiles to predictable C, and the reason you can do that is because it allows all of the C idioms. So you allocate memory, free memory, bump pointers, play with your stack, do whatever you want. All of that is supported within ATS, and it's type safe. So aside from tail calls, and one other thing which I'll get to at the end, there's no real magic going on, that turns code into efficient runtime. And the reason it's able to do that is because it has a very rich linear and refinement type system and a proof level language. And I think that of all of the things that, of all of the attributes of ATS, I believe that this is the one that is the most important because it shows that linear and refinement types are things that are good independent of just controlling memory. In ATS, linear and refinement types are not just for memory. You can track anything with that type system. You can track a file handle, you can track a database handle, track network handles, you can track your Oz instances, any resource that you want to keep a track of, you can use the linear system to do that. The downside is ATS is an extremely difficult language to learn. By orders of magnitude, this is the most difficult language that I've ever had to pick up in my life. Still, it was true 2 years ago, it's true now. The syntax is ugly, I guess. I mean, and there's a lot of it. There's a ton of it, and the error messages are just insane. It's like looking at the Voynich manuscript or something. It's crazy. And also, the compiler itself is not super mature, so it still generates C code that sometimes GCC will refuse to compile, right? So, stuff like that. But again, this is a research language, right? So the job of a research language is to present ideas, and that's what I think you should take from ATS, is to mine it for the ideas. If you're a language designer, please steal this stuff that I'm going to show you, if you like. If you are a user, the next time you evaluate a piece of technology, the next time you evaluate a language, please ask about this. Ask about why, ask why the language designer has chosen not to include a linear type system in their language. There's probably a great trade-off, but it should, the user should be able to ask why that trade-off was made. For reasons that are not ergonomics or something like that. So I spoke about ATS previously a couple of years ago, and mostly talked about it at sort of this high level. There were examples there. There was sort of more like a survey talk. Not very interesting examples, but they were there. But today I want to get into more of the interesting features. And for the reasons that the syntax is, there's a lot of syntax and all that stuff, I have to show you this giant wall of code in this presentation. The exact thing that you're supposed to not do in presentations, which is a slide full of code, is what I have to do right now. So I kind of sweep this under the rug of, well, I called it a tase, so this all goes under there. But I'm going to slow reveal the code, but it's still going to be a giant wall of code. And also, I'm not going to explain every piece of syntax because if I do, there will be no time for other speakers after me. So I'm going to hand wave a lot of this stuff and just move on. But rest assured, all this stuff works. It's in my GitHub repo. And if you really want to know how something works, please ask me afterwards. So at a high level, before we start, we need to understand what linear types are. This is just a very high level explanation. It glosses over a lot of detail. A linear type is a type that only gets used once. You pass it to a function, the function consumes it, and it's no longer available. At a very high level, that is a good enough definition to get started with. There's a lot of subtlety between linear types and affine types and things like that, but I'm not going to get into that. This is what I need right now to show how the examples work. So the first example I want to look at is reading from a file and using the linear type system to track the file descriptors. So you close them, right? And using the CFFI to do various things. So here's what that program looks like. This is not the Tase part. The Tase is coming up. So I'm opening I'm opening the same file twice. I am creating an anonymous function. I'm passing the anonymous function along with that file descriptor to some function, and then I'm closing the two file descriptors. fopen is a very simple wrapper around C's fopen function. I think that's in stdlib or something like that. It just takes a path and it takes some permissions. fopen returns this linear data type. That's what data v type means, a view type, called file handle. And this is how the linear type system knows to track it. So anything that is declared with a data v type is a linear type, and whatever gets stuffed inside of there is tracked by the type system. So you have to consume that somehow, whether it's freeing it, closing it, doing whatever. So we're back to the original code. And notice that for every fopen, there is an fclose. And the reason for that is what I just said before, because it's returning a file handle. If you do not close it, close takes that file descriptor and consumes that linear resource. So if you do not close it, there's a linear resource hanging around at the end of the program, and ATS will complain. You will get a type error. It's a very rude type error, but you will get a type error. And the same with that. So fopen looks just like that. So it's taking a string and a mode, which is like read or read write or whatever. And at the heart of it, it's really just a call to fopen in C. So that's what the extf call means. I think that stands for external foreign call. I've stopped trying to figure out what ATS keywords mean or where they come from. Just go with it. I don't know why there's a $sign on this one in particular, but just go with it. So fopen takes the path and the mode and returns a pointer. Here I'm ignoring like, negative ones and things like here I'm ignoring the fact that the file may not exist, all that stuff. So now I can take that pointer and cast it to a file handle. This is a safe cast because a file handle and a pointer have the same representation in memory. They're both just pointers. The file handle is just an abstract type. There's no boxing or anything like that, so I can convert back and forth pretty easily. Using this thing called a cast function. It's another keyword, castfn, and also extern. But I don't know why extern is required there, because extern is only needed for things that are actually extern to like external modules and stuff. So, but this got it to compile. So we're fopening test, we're fopening it again, and now we're actually creating an anonymous function. So this, by the way, I'm not going to harp on this too much, but this is actually a stack allocated closure. Very few other systems programming languages allow that. This is allocated on the stack and automatically freed when it goes out of scope. And I think this is probably one of the only stack allocated things, are probably the only things in ATS that are managed by scope. So once it goes out of scope, you can't use it, even if you have a linear type for it. In fact, it won't let you keep that linear type beyond the scope.
Is this a return to Fragen's notation?
I have no idea who that is.
Okay.
So f with line is a function that takes that file descriptor and that closure that we just passed in, or that we just created, and that's what it looks like. So it's a function that takes a file handle and a reference to a closure. That is a reference that will go away. And by the way, this is all safe. You can't have dangling stack pointers in ATS because the type system makes sure that that reference cannot be accessed outside of scope. And at the end of the day, it's just a wrapper around GetLine. GetLine is a standard C function in stdlib or something like that. And it takes a length, which if it's initially set to 0, along with a buffer that's a null pointer, it fills up that buffer with that initial line. This is not obvious from the API. You just kind of have to read the documentation and know that, but it's a standard C function. And it takes that file handle, coerced back to a pointer. Again, safe coercion because they have identical representations in memory. And it's a cast function, which again is extern for some reason. And we're calling f on that buffer. It was a null pointer. Now it has a line inside of it. We cast it to a string, and f does whatever it needs to do with it, which in this case is printed out. All it does is print the line. And then we call Fclose, which again, just like fopen, is an external foreign function call to Fclose in exactly the same way, converting a file handle to a pointer and then passing it along and returning a void. This consumes the file handle, and we call it again on beat. Anybody notice anything in this? Anybody catch anything? Yeah.
You use the file handle twice.
Where?
Once in output line and once in close.
Exactly. Well done, sir. Well done. And that's my next slide. Here's why. Because the f with line, the file handle has a bang in front of it. See the bang? The bang means this resource is not consumed. That's so you can leave a resource unconsumed. You don't have to you don't have to be restricted to this like linear type system thing. Fclose has no bang, so therefore it's consumed there. That's why. Well done. I wish I had things to give out. Right? So I think what we've learned from this example is that linear type systems are definitely not just for memory. We use them for memory, and we can also use them for a file handle. The C foreign function interface is extremely easy to use, and it's very much encouraged in ATS. This is opposed to a lot of programming languages where like the unsafe bits are sort of like just things that you do when you have to. In ATS, it's very much encouraged and used because ATS has very strong roots inside of C. Even though I say that the linear type system is sort of this thing that you can sort of think of like independent of memory, they are very well integrated in ATS for a reason because ATS was designed as a systems programming language. So foreign function calls, not a problem. If something messes up, just open GDB. It's not that hard. So now we're going to look at a slightly more complicated example. This is a linear tracked array. We're going to build it up from scratch. A linear tracked array is just an array in C. It's one of the most fundamental things that you can do in C, just a contiguous chunk of memory. So we're going to see how you track that linearly using data types and linear views, and most importantly, proofs. We're going to look at how we interleave proofs in code, like bring proofs into scope explicitly. So this is what a data type definition for a linearly tracked array looks like. Taking away some of the complexity, we have an array type that is parameterized on that. VTFLT means another view type. I have no idea why it's not just called a view type. I think it stands for a view of a typed flat. I don't know what that last D stands for. Sorry. I told you I've given up on figuring out what these things stand for. Adder is an address. It's an abstract address that the thing points to somewhere in memory. And int is actually a type track length. So as you cons onto this array, that integer gets incremented at the type level. So for nil, it just takes an abstract address. By the way, that is a refinement type. And a length of 0, which is what you would expect. A nil array has a length of 0. A cons array takes an address and some n of type nat, and nat is actually nothing more than an integer that has a refinement that it has to be greater than 0. Nat is just there as a convenience. It's not built into the programming language or anything like that. So it takes some view type, some address, and n+1, because when you cons onto something, you have an n+1, and returns an array, it recurses and returns an array type that is an A, and the address is L plus the size of A. So the size of a thing is known at compile time, right? It's known at type check time, so that abstract address plus the size of A is now the new address. and n. So by the way, this n plus 1 and n thing is kind of like, anybody remembers n plus k patterns in Haskell? It's awful, isn't it? but that's how that works. So very verbosely, you can construct that array at the bottom, ABCD, that way. The array cons, right? Forget about what that string 0 copy VT thing is doing. It's essentially just allocating that A on the heap, which is what you need to do if it's a view type. That's linearly tracked. So what I want to do is now I want to split this array. So I have an array of ABCD, I want like ABCD or something like that. But I want to statically split it and prove that that is correct. Right? So I have this array of, this array cons, ABCD. And then I have this type level proof. It's a type level proof function called array split that takes that array and a type level number, in this case 1, it could be anything, it could be passed in by the user, and outputs a proof, 2 proofs, A1 and A2, such that A1 goes from the beginning of the array to I, and A2 goes from that point to the end of the array. So now you have a proof of, you've taken a proof of 1 array and split it into a proof of 2 arrays. And now you can pass that to whatever you want. So print A1 and A2 separately, you can do that at one time. And all of these proofs are erased. This is all just type level stuff. So you can pretty much imagine that that line starting with PR val and everything up to print array is just not available at runtime. It's just invisible. Unfortunately, AR split, this is the Tase part, is a little bit verbose and dense. But at its heart, it's a proof function. That's what that PRFN means. By the way, there's also a PRFUN keyword, which means that it's possibly recursive, the proof function is. And in that case, you actually have to give it a termination metric, which is why you have a PRFN. But we won't get into that just now, which is why the PRFUN down there is. There's a lot of keywords. So array split, call split, which delegates that inner proof function split. Most importantly, we have the arguments. The arguments are a proof of an array starting at some address L with some length n, I, which is the size of some length n, statically known, and the return type is a tuple of an array starting at address L of length I, and an array starting at L plus I times the size of A. That means bump that I number of times in the array, start there, and go to the end. And the length of that array is going to be n minus I. And this is all statically proven. And we're saying that we have a refinement type that the I that you pass in has to be less than the length of the initial array. So if you don't do that, you get a type error. So you have to prove to the compiler before calling this proof level function that the thing that you're passing in is smaller than the size of the array. And some boilerplate things like the view type and the address. So we're calling split. And this is split. I've deleted a bunch of arguments. The essential structure is split is an if-else. If I is greater than 0, do something. Otherwise, do something else. So the first thing it does is uses uncons. Uncons is not a proof level function. It is a praxis, which is another keyword. And a praxis stands for proof axiom, which means that I'm not going to prove anything, just go with it. This is an unsafe head at the proof level, right? That's what this is. So we've already proven that I is greater than 0, so we know that it has to be an array that has something on the head and the tail. All this is telling you is at the proof level, split that out for me. So it's taking an array of A, L, N, and it's handing you back an array. It's handing you back the initial A and an array of that minus 1. So it's just saying just do it. Yeah, I know it works because I have that I greater than 0. So this is the proof level language. Obviously, this is not as tight as like Coq or all of those other things, but he calls it a pragmatic proof language. We'll just, I guess, go with it, I guess. And we have a split. We recurse on split and pass an n minus 1 and I minus 1 as template parameters. And we pass in the tail of the thing we just split, and we get back a left and a right, right? And now we can build that array back up. So we have this array cons, which constitutes the left side of the array, going from L to I, which is the initial head, and the left, which constitutes the tail, and PF right, which is the rest of it. And now we have what to do in the else case. In the else case, I is 0. And so we have this cute thing called EQ make, EQ int make, which is a proof function that checks to see if x and y are identical, and if it does, if they are, or are equal, assigns it a data prop constructor, yet another keyword. So what a data prop is what a data type is at the term level. So ATS has sort of sum types at every level that it operates on. So it has a sum type for at the term level, which is a data type. There's a sum type at the type level, which is a data sort. There's a sum type at the proof level, which is called data prop. And that's as far as it goes, by the way. There's no more after that. So once you have this proof that x and y are equal, you can assign it that EQ and constructor. By the way, the only reason I'm doing this is to show it to you. There's no reason to do this. I just wanted to show you the ATS. So I'm swallowing the constructor, and now I have an array nil being returned back. So at the essence, what this proof thing is doing is what you would do at the term level. Like if you're doing functional programming, just sort of iterating over a list. Yeah, it is a fold. It's a proof level fold over a list up to a certain point. That's it. That's all it's doing. So there's this sort of correspondence between, very tight correspondence between term level programming and sort of type and proof level programming in ATS, which is good. So now we have array cons, and we call array split on it, splits it out into two things, and I can print it out. No problem. So what we've done here is we have a fundamental low-level concept, arrays, which are everywhere in C. Like you have to use arrays if you're going to do C stuff. We've made it type safe. There's no loss of performance. The equivalent C code would run as fast. You can make ATS code run as fast as the equivalent C code. And you haven't really lost intuition of that either, right? If you're a C programmer, yeah, a lot of the syntax is going to take a while to get familiar with, but you're not going to have to completely redesign your program. This isn't a forget everything you know about programming, here's ATS. It's, okay, keep the stuff you know about programming, now prove it to me. That's what ATS is. And there is no term level magic. There is no like runtime magic that makes arrays do the right thing. It's all, I mean, more or less, I don't know. I hate to use the word obvious, but you can reason about it, just using the code. And also, by interleaving proofs, bringing proofs in manually, you can have very flexible design. So in Haskell, you have this, right? You have like explicit constraint passing. You can bring in constraints manually via a function. But that's a hack, and this is way nicer. And that's actually a pretty good hack. It works pretty well, like in real code. But I would much rather have this than that. But just this part, not ATS. Please don't put ATS into production. So sort of the last thing I wanted to show you is streams. ATS streams are sort of a relatively new thing. And this actually does have runtime, compile time optimization magic in it. But the compile time magic is the same. It's no harder than arrays. You still use the same refinement types and things like that. Nothing new has been really added. So but there's a bunch of magic at runtime. But the memory usage seems to hold steady. I'm not exactly sure what it does. I think like compiles down to like this network of go-tos or something like that. But that's pretty much it. So here's what a data type for streams looks like. You have a stream nil, you have a stream cons, and it constructs a stream VT, which is a recursive data type. You can have two data types that are recursive in ATS, which is a list VT, which is just a pointer, back to a stream VT con. So basically, In the cons case, it's just a level. It's a level of boxing to the next constructor. I mean, to the next console. And it introduces a new keyword called L-delay. Again, I have no idea why this one has a dollar sign in front of it, but it does. So L-delay is a pair of some suspended computation, and you optionally free the linear resource after that. If there's a linear resource to be freed, you free it there. And that's really all there is to it. And there's a bang that forces one thumb. This is not quite as sophisticated as Haskell's lazy evaluation because it doesn't do like weakhead or anything like that. It just kind of evaluates the entire thing there. So if it's a box type, it just evaluates the whole thing. But yeah, that's how delays are done. That's how streams are constructed in ATS. So if I just wanted a stream of numbers, this is a function that just starts a stream of numbers starting at 1 to however long. I have a number stream, I have a loop, and I kick it off with some current thing, and then I delay the stream constructor, and within that thunk, I recurse on loop again. So every time I force it, I get a stream console, and I take one thing off the top of the console and it just keeps looping lazily, which is what you're supposed to do. So as a non-trivial example, wanted to show you how to generate like Pythagorean triples using just streams. So Pythagorean triple, if you're not familiar with it, is any three numbers such that a squared plus b squared equals c squared. So it's like the two arms of a triangle, right angle triangle. 3, 4, 5 is like I think the smallest example. So the idea is not to be clever. The idea is to generate all triples, starting from 1, 1, 1, 1, and generate all of them, but only keep the Pythagorean triples. So this is a standard sort of like brute force benchmark that people use to test like streams and things like that. And ATS has the same performance as C and C++. I know that because I tested the best ones that I could find, and ATS is exactly the same. And this is how it does it. So the thing to note here is not so much all of the +1s and -1s and all of that stuff. That stuff is just by the way. What I wanted to show you was this guy, this network of functions. So F1 is a stream function. F1 delegates to F2. These are all mutually recursive. F2 delegates to F3 possibly, or back to F1. F3 either delays the thunk and passes back to itself, or forces an F2 inside of that thunk when it's forced. So there's a lot of like mutual recursion going on here. And the point is that ATS is able to like take this and convert it into like very efficient code. I think now that I think about it, the reason it's able to do that is because all of these like mutually recursive things are in the same function. So it can see that and turn them all into go-tos. I think if they were all separated in different modules or something like that, it might not be able to do it, but in this case it can. So here I have a filter function that takes all of the triples and some lambda, destructures the triple x, y, z, and just makes sure that x squared plus y squared equals z squared. That's it. So it's a stream of all the triples with a filter in front of it that makes sure that only the ones that we want pass. And on my machine, it stays steady at 688 kilobytes of memory. And I think most of that is coming from that lambda closure, which allocates on a heap. So if you think about it, 3 integers, or what is it, 64 bytes an integer multiplied by 3, that's like the minimum amount of memory you have. I think the rest of it is has to do with like file descriptors and printing to the screen and things like that. But 688, steady. And even without the filter, you take the filter out, you just generate all of the triples and keep going. It's still 688. All the filter does is make it slow, which is what it's supposed to do. So that's essentially the end of my talk. I think that some takeaways are that linear types and explicitly bringing proofs into scope and having first-class access to those proofs is a great idea. And none of this stuff is new. People who design type systems people who design languages have access to all of these things. They're using these things at some level inside of their code, but they're not exposing them to you. And I think that ATS is at least one anecdote or one piece of anecdata that suggests that exposing that stuff to the user is not a bad idea, and we can do cool things with it. So I think that users are sophisticated enough to deal with this problem. The hard problem, of course, is UX. I mean, so it's easy to throw these ideas out. The hard part is making them nice. When ATS doesn't do much with that, but that's not the job of an academic language. It's the job of industry adopters to make things nice for industry and make them a product and all of this stuff. And also, last but not least, it just shows that FP does not have to be slow. I think FP still has a reputation for being slow, I think. And I think ATS is at least one positive story there. So, great. That's all I have. Thank you.
Right, any questions?
We saw that there are a couple of different kinds of ways that you can call a function with a linear argument. Do you have an idea of how the expressivity of ATS when it comes to like linearity and affinity compares to the borrowing system in Rust?
Yes. Okay. So in ATS, you can keep linear types around for as long as you want, and you can free them at some point later. You are not restricted to having to free them once they go out of scope. If that makes any sense. In Rust, Rust automatically frees a resource once it goes out of scope. So that part is like baked in for you. So the way that ATS deals with stack variables is kind of the way that Rust deals with all resources, which is just kind of prevent access to them after they go out of scope. Does that even address your question?
I think so, yeah.
Okay.
Thanks.
That's one example. I can't think of others right now. I think maybe others are like Rust doesn't have like a low-level like L delay type mechanism, so the iterators are, I believe, part of the language. I think I'm not sure. So as they're sort of built into the language, and here it's just sort of a primitive. I mean, that's not the primitive. The primitive is below that.
Cool. Thank you.
So you kind of sold me on the linear and refinement types the first time I saw the talk you gave about this, and it made me go back and read some more of the PI behind ATS's work. And the thing that seems really interesting, but I don't understand even a little bit, is the multi-party like logic and session type stuff that he's talking about now. Have you looked into that at all, and do you have any thoughts, or is that just kind of too galaxy brain complicated for anything at the moment?
I have looked into it. I stopped looking into it because there wasn't a runnable example that I could find. And
Okay.
I have a policy where I don't look into things that don't have runnable examples. So it seems pretty nice, and maybe someday I'll go back and try and build one myself. But that's where we're at. That's where I am.
Thanks.
What in your mind is like the top UX problem that you've encountered with ATS?
Oh,
like the
yeah,
thing
let me
that's
show
the
you. Hold
hardest to deal with?
The top UX problem is that's a nice type error. This guy is just an awesome typer. You want to see this? This is good stuff right here. That's about, I don't know, 5 times smaller than what you would get if you were actually doing real stuff. I think. What is it actually saying? Oh yeah, it's actually if you can parse that, it's relatively straightforward. What it's saying is that there's 2 linear resources that you haven't consumed. That's all that's saying. Like this A1, whereas let's see if I can. Yeah, there's an A1 here. See that? And an A2 there. You haven't consumed those. Type error. So I don't know. Was there something else that that you wanted to see? Yeah, but it gets a lot worse when you make mistakes at the proof level because you have like unsafe operations like praxi and stuff at the proof level. And yeah. Yeah.
I was just wondering, so this is all user allocates and frees memory?
Yes.
Okay.
Yeah. Hmm. Not always, but for the most part. You can do it that way, but there's convenience data structures in ATS that do it for you and take it away and all that stuff. But
So is it common to use like the linear types to like make sure that you free memory that you've allocated?
yeah, all the time.
When you were showing us the implementation of the read file function, we went from having some uninitialized memory to having initialized memory. Is there something in the type system that's making sure that you don't like use memory that hasn't been like written to yet, that you just skimmed over, or is that just not checked yet?
Which part are you talking about?
The buffer that is being written
yeah.
to.
That is totally unsafe. Like
Okay.
so, like what I did there is what the C function expects to have a I think star char star buffer that if it's null it fills it up. So this is outside the scope of ATS to like make sure that that's initialized or not. If it isn't, then you just segfault. But things inside of ATS, yes, you have to initialize that memory.
What language is ATS actually implemented in? Is it self-hosted or is it implemented in C
Um,
or something else? I don't know.
This goes back a ways. I believe that the original ATS was implemented in a thing called dependent ML, also written by this author.
Okay.
And since then, there have been 3 different iterations of ATS, each written in the one before it.
Amazing.
You're looking at the latest one.
How many lines of code is the implementation, and has anyone tried to implement it in something else?
I know that Vanessa McHale has, God bless her, has taken on the task of trying to write a parser for ATS. I don't know where that effort is at this point, but no, there's nothing except what he's done, as far as I know.
Okay, thank you.
I wish there was.
Yeah.
Yeah. All right. Thank you.